me start this whole sentence over. I originally wasn't going to paint Douglas Adams, but then I decided who better to paint since Douglas Adams started this whole debacle. I've already laid down a mid-tone on his face, but that's okay, I think. I don't think anyone will really mind that much. So yeah, Douglas Adams did start this whole thing that I'm doing right now. Because I want to study four-dimensional geometry, and Douglas Adams said that if you want to understand something, if you want to, be sure you understand something, try to explain it, or explain it to somebody else, teach it to somebody else, and that will kind of further it. You know why. You know why that's a good idea, right? Yeah. So, that's what we're doing right now. I am painting Douglas Adams, and I'm talking about four-dimensional geometry. Because why not? That's what I want. I decided that I want to understand four-dimensional geometry, and I decided that I like painting Douglas Adams, and I remembered, well, I was painting Douglas Adams because I'm losing my words again. This happens occasionally. See, this is why I want to like try to make it as a writer, but it's not gonna work because I don't have any words, and I have no words for anything. It's like, oh, your house burned down? Yeah, cool, have fun. I don't have any words for anything. So here we are, painting Douglas Adams while I struggle to communicate what I'm doing. That's what's happening right now. Anyway, so I usually just kind of ramble aimlessly about whatever it is I'm writing about, but today I will be rambling aimlessly about four-dimensional geometry, which is a very cool bit of geometry, right? Geometry is really cool, and if you don't like geometry, then you can still stay here and try to learn something too, right? You can stay here and we can talk about geometry together, four-dimensional geometry. So I guess we're just going to start with regular four-dimensional, we're just going to start by, I'm going to try to explain what I know about four-dimensional geometry to you. So that's what we're doing right now. So, essentially what four-dimensional geometry is you take three-dimensional geometry and you add another Euclidean plane. It's really that simple, you guys. Dang it, I was on the wrong layer like a smart guy. Okay, there. Yeah, so I was just kind of fixing his hair here. I kind of messed it up. I'm so sorry. I am a disgrace. Yeah. Oh, I also had the wrong color selected. Whatever. I think this was supposed to be going here. I believe that's where that was supposed to be going. Let's see. Yeah, that's supposed to be going here. I'm kind of dumb. Anyway, so four-dimensional geometry, really cool bit of geometry. All geometry is cool, but four-dimensional geometry is really cool. Yeah, so what I was trying to say was that it's essentially you take regular three-dimensional Euclidean geometry and you just shove another plane on there and you got four-dimensional geometry, which is fun. I think it's fun. I don't know, maybe you don't. I do. Yeah, so just adding planes. Okay, let me try to find my words again. Let me try to get some. Okay, yeah, so to start this off, we should probably talk about, like, the different shapes. So, we have in two-dimensional geometry, we have the circle, and then in three-dimensional geometry, we have a sphere, and in four-dimensional geometry, we have what could be called a globe or a hypersphere, just depending on how you want to say it. If you want to call it a globe or a hypersphere, it's your call, I guess. I mean, it's like the same thing. I'm sure people will know what you're talking about either way, so it's whatever. It's your call, man. You can call it whatever you want to. that is that is the beginning of four-dimensional geometry, but that is introducing you to one shape. Yeah, so and then, we have the edges, and in three-dimensional geometry we have faces, in four-dimensional geometry we have facets. And in two-dimensional geometry we have area, volume, and then content. So that's essentially the important stuff, or not the important stuff, but the basic shape stuff that you should know before you kind of dive into four-dimensional geometry, right? So also a good way, if you I don't know, like, not really a good way, but like if you want to remember things and you don't want to remember like tesseract, pentatope, polychron, 16 cell, if you don't want to memorize all of that, most of the time you can just stick hyper onto the front of whatever you're saying and it means the same thing. So you can just tack hyper on there and you should be fine. Just for the most part. Like, that's not going to be for everyone. Like, we've got the cross polytype instead of the 16 cell, and the simplex instead of the pentatope, which you can't just shove hyper on and be fine. But for the most part, you can just drop the word hyper in there, hypersphere, and you'll be good. People will know what you're talking about, which is cool, I guess. I don't know. Do you think that's cool? Anyway, so what I'm talking about now is hopefully four-dimensional geometry. That's the whole point. That was the whole reason I started this live stream, was to talk about four-dimensional geometry. Okay, I'm gonna have to turn this up to 100 just to kind of really manipulate these edges here. Sorry, I'm kind of focused on these edges. Okay, I think I got it. Yeah, so four-dimensional geometry, very cool. I need to stop saying four-dimensional geometry and just tell you what I'm talking about. That's not right. Anyway, so I guess what we should talk about right now is I don't know, you want to talk about sphere stacking? Should we talk about that? I don't know. Let's start with so essentially, like, one of the coolest things that you can do with four-dimensional geometry is or what I think is one of the coolest things you can do with it, at least, is make Klein models. So a Klein model is essentially two Mobius strips folded together in such a way where instead of self-intersecting, they cross they don't self-intersect, they cross the fourth dimension, which is pretty cool. Like, I think that is the most rad thing I've ever heard in my life. That's so rad. So that's where we are right now. Over here in four-dimensional. Yeah, so a good way to kind of visualize four-dimensional geometry, if you are struggling with kind of imagining another spatial dimension, a good way to kind of think about it is to imagine you are a two-dimensional being and someone took a two-dimensional cross section. No. You are a two-dimensional being, and so every time you see a three-dimensional object, you would be looking at a two-dimensional cross section of it. No, you would be looking at a one-dimensional cross section of it. So a two-dimensional being would see a one-dimensional cross-section of a three-dimensional object. And that's the same thing in 3 dimensions. We're seeing two-dimensional cross-sections of three-dimensional objects normally, because we're seeing two-dimensional cross-sections of three-dimensional objects. So in 4 dimensions, we would be seeing three-dimensional cross-sections of four-dimensional objects and all that. So in 2 dimensions, back to the two-dimensional example, if you took a 3D object and put it in a two-dimensional plane, which would just be, an X and Y plane, and you took, say, a hand or a ball. Let's start with something simple. Let's say a cube. So we took a cube and we decided that we were going to put it in the two-dimensional plane. We would see so us being three-dimensional would see a square, but the two-dimensional people or beings, whatever is there, would see a line, because they're seeing everything in one dimension because they're two-dimensional. Just like one-dimensional beings would see everything in 0, which is points. They would see everything in points. So that's kind of where we are right now, right? We're seeing two-dimensional objects as, what am I saying? What am I saying? We're talking about seeing three-dimensional objects as 2D cross sections. Yes, so we would see a four-dimensional object as a three-dimensional cross section, but projected into the three-dimensional plane, we would be looking at it as a 2D cross section. So if someone were to drop a tesseract into our plane and rolled it through the third dimension and back from the fourth dimension through the third and back into the fourth, we would see an infinite, I can never say this word, infinitesimally. I have a hard time with that word. I can spell it, but I can't say it. But yes, so you would have that, a really small point. There you go. That gets the point across. That was a terrible joke. I'm so sorry. You would see a really small bit there, and you would and it would expand into its full size, and then it would shrink back down. Just like if we took a cube and put it corner first into the two-dimensional plane, we would see a point expand into a square, a full-size, like rhombus-looking bit, and then it would shrink back down to a point, and it would look so weird for the two-dimensional beings that are, looking at that. But for us, it would look normal because that's kind of what we're used to seeing already. Right? Well, no, it's not. But we wouldn't think anything was weird about it because we're kind of used to seeing three-dimensional objects behave that way, like rolling through the plane. So you have to imagine four-dimensional objects in the same way. So you have to imagine the tesseract rolling or hypercube, whichever you prefer. You have to imagine it beginning in as a point and expanding into a 3D cross-section of the tesseract and then shrinking back down, because we would see all 4 dimensions of it, but we would see it in 3, right? So we're seeing every bit that it has to offer, but we're seeing it in 3 dimensions, if that makes any sense at all. Like, it's kind of really tough to explain, which is why you shouldn't need a prerequisite to a live stream. But that's what's happening right now. I was about to go say, hey, everyone, go read Flatland. But no, we're not doing that right now. We're not doing that. We don't have time to do that. So, yeah, so, you don't need, this live stream does not need a prerequisite. So, what we're talking about right now, right, is I'm trying to explain the 4th dimension to you. So we have 3 dimensions. We have X, Y, and Z or Z, depending on whichever way you like that more, Z or Z, Z or Z. Anyway, we have the 3. So 4 dimensions just adds the W plane. So, and we're talking about 4 spatial dimensions right now. So some people do say, oh, well, we live in 4 dimensions right now. You know, we have 4D space-time, blah, 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 blah. Yes, we do have 4-dimensional space-time, but that is only if you aren't taking this live stream in the spirit of Douglas Adams and you don't believe time is an illusion, which here on this live stream we do. Well, I do. Don't know about you guys, but time is an illusion. And I've, known this for years, but, Douglas Adams really did reinforce that. No, he didn't reinforce that belief in me, but he did, what am I trying to say right now? Let me think about that. I'm trying to talk about what 4-dimensional geometry is, what it is. That's what we're doing right now. We're not talking about Douglas Adams. We're not talking about the Hitchhiker's Guide. Gotta remind myself. Gotta, calm down and start thinking about 4 dimensions. So let's talk about the Platonic solids. Yes, you can't go wrong with the Platonic solids. So, the Platonic solids, we've got, they're called the regular polytypes. So in 2 dimensions you have infinite, and then here we've got the 5 Platonic solids, right? Here in two dimensions we've got the 5 Platonic solids, which are, the 5 regular polytypes. Sometimes they're called the dice. They're the objects that, if you play Dungeons and Dragons. Huh? Yeah, sure thing. Yeah, so if you play Dungeons and Dragons, they're the regular 4-dimensional. What am I talking about? A 4-dimensional game of Dungeons and Dragons would be crazy, though, because they have 6 Platonic solids, which is 1 more than we've got here. They have 6 Platonic solids, which is really cool. But that's not what we're talking about. We're talking about the 3-dimensional Platonic solids. I gotta remind myself sometimes. I gotta keep myself focused. What was I saying? The Platonic solids. Yes. So the Platonic solids that we have are, we have the cube, the obvious one, dodecahedron, and I'm going in order of my least favorite. Yeah, my least favorite to my favorite. So I've got the cube, the icosahedron, the dodecahedron, the octahedron, and the tetrahedron. Yeah, so that was my, least favorite to favorite, Platonic solid. They're very cool, Platonic solids. And, they are the regular polygons that you can stack, you can take. So, like, for example, a cube, everyone knows what a cube is. It is 6 squares folded into the 3rd dimension. And, the tetrahedron is 4 triangles. The octahedron is 8 triangles. The dodecahedron is 12 pentagons. Icosahedron is 20 triangles, stuff like that. So those are the Platonic solids that we've got here. And then in 4-dimensional geometry, going in order of my least favorite to my favorite, we've got the 24 cell, which has 24 octahedral bits, faces. And then we have the most confusing one of all, the hypericosahedron, which is the 600 cell. We have the hypercube or tesseract, the hypertetrahedron, and the hyperoctahedron. So yeah, those are the 4-dimensional platonic solids. So, of course, the added one that we don't have here in three dimensions is the 24 cell. Well, we don't have any of these, but the one that doesn't parallel is the 24 cell. Yeah, it's the 24 cell. That's the one that doesn't, parallel, right? So also something really weird. So starting from 2 dimensions and working our way up. So to go 2, 3, 4, 5, 6, to infinity. We have numbers of platonic solids. We have infinity, 5, 6, 3, 3, 3, 3, 3, 3 forever, 3 from 5 onward, it's 3 platonic solids. And that is so funky, right? Why? That is so funky to me. 3 platonic solids from 5 dimensions onward. Yes, so that is what we're talking, those are the platonic solids. So let's kind of talk a little bit about the 600 cell, shall we? The 600 cell is just, it's a weird looking thing. It's like really scary. If you look at an animation of a 600 cell rotating in 4 dimensions, but you look at the 3-dimension, well, it's actually a 2-dimensional cross section of the 3-dimensional cross section of the 4-dimensional object. But if you look at it like rotating, it's terrifying. It's absolutely horrifying. Like, it scares me and it haunts my nightmares. Anyway, I need to like kind of get painting. Yeah, but that thing is absolutely like ridiculous in size and shape, and the way that it rotates, it's terrifying. Like, I've said that like 6 times, but you know. So it has 600 tetrahedral faces. 600 tetrahedral faces. Can you even comprehend that? That's 5 tetrahedrons to an edge. 5 tetrahedrons to an edge. That's mind-boggling. Like, that's insane. So, of course, where those would overlap in 3 dimensions, you would slide them along to the 4th dimensional bit. And it has, get this, 120 vertices and 720 edges. That is mind-blowing. That's mind-blowing. So the 600 cell, it makes me want to cry. I absolutely hate it. It's terrifying. And so it's terrifying. It's just, that's the 600 cell summed up in one word. Terrifying. Now we can talk about the hyperdodecahedron, which is otherwise known as the 120 cell, which is slightly less terrifying than the 600 cell. So it is a finite, of course, 4-dimensional polytope. So it's, and it looks wonky rotating as well, but it's not anywhere near as terrifying as the 600 cell. That will scare me for the rest of my days. Like, every day I spend on this planet, I am thinking about how terrifying the 600 cell is. It's freaky. It's really freaky. The 600 cell, it makes me, like when in the Rocky Horror Picture Show, when they're singing about Eddie, and, they say, what a guy makes you cry. And I did, Yeah. Well, the 600 cell, what a guy. Makes me cry. Makes me cry. Yeah, it does. It's terrifying. 120 cell, slightly less terrifying. It has 120 dodecahedra, only 3 to an edge, 720 pentagons, that is, 720 pentagons, all wrapped up, bundled, and ready to spin into your nightmares. It's a terrifying, terrifying little, it's not little, it's a terrifying shape that is, absolutely horrifying. Kind of like how my painting looks right now. Like, my paintings kind of always look really scary. Let's put this on 42. I keep it on 42 usually, but I feel like I should especially have it on 42 right now because, well, look who I'm painting. The guy who said 42 was the funniest number. The funniest 2-digit number. It's the funniest 2-digit number. And guys, there are people who, think, wow, 42, that's a real nice number. That must have some sort of meaning. It doesn't. It's not a joke in base 13. Douglas Adams made that very clear that it is not a joke in base 13. This guy does not make jokes in base 13. Maybe next time I do a live stream, we'll paint someone who does make jokes in base 13 and we'll talk about base 13. Because base 13, ooh, that's a funny number system. That's a good number system right there. If I've ever met a better number, I've never met any number systems. If I've ever seen a better number system, I haven't. It's just a fantastic number way to, count and keep track of things. It's a great thing. It's pretty neat. Yeah, so, when Eddie said he didn't like his Teddy, you knew he was a no good kid. But when he threatened your life with a switchblade knife, what a guy. Oh, I've got to do some Rocky Horror fan art. How have I not done Rocky Horror fan art yet? I've watched that like 10 times maybe. I think I've actually watched it 6 times, and I found out about it about a month ago. Well, I didn't find out about it a month ago, but I watched it for the first time a month ago. Guys, it's so good. If you haven't watched Rocky Horror yet, just get off this live stream and go watch it. It's fantastic. It's just great. Rocky Horror, absolutely amazing. I love it a good bit. Not as much as I love The Hitchhiker's Guide, but that would be pretty tough to kind of recreate my love for The Hitchhiker's Guide. The Rocky Horror Picture Show, though, very, very, very close. The Rocky Horror Picture Show, it's just really good. You should check it out whenever you get the chance to. And if you don't get the chance to, just make a chance to do it. It'll be worth your time. And if it's not, then I am so sorry for having wasted 100 minutes of your life. You will never get it back. And I give you permission to come fight me. DM me, I'll tell you my address, and yeah, you can come beat me up one time. But what I won't let you beat me up over, because this is irresputable and undisputable. You can't dispute this fact. That's how much of a fact it is. And that fact is that The Hitchhiker's Guide is fantastic. You should read it. It will not be a waste of your time. And after you read it, you should listen to the radio show. Or listen to the radio show first, whatever you dig. The Hitchhiker's Guide, all of its forms are equally fantastic and equally confusing and equally contradictory. It's just a great bit of my life was spent with The Hitchhiker's Guide. But anyway, that's not what we're here to talk about today. No, it's not. We're here to talk about what? 4-dimensional geometry. How do I keep forgetting? That? 4-dimensional geometry. That's what we're talking about today. Nothing else. See, my brain, it doesn't work, and I forget what I'm doing all the time, constantly. Yes, so what I'm doing is talking about The Hitchhiker's Guide. So that's my default setting, I swear. The Hitchhiker's Guide is my default setting. Yes, so let's talk about a really simple shape to kind of get our minds off of the terrifying ones. Let's talk about the pentatope. It's the simplest 4-dimensional polytope. And it's called a 5-cell because it only has 5 vertices. It's a pretty cool thing. It's a simplex. It basically looks like a tetrahedron. It's very cool. Let's talk about the simplex. So, yes, simplex, the hypertetrahedron, if you will. Yeah, it's pretty cool. So a simplex is a line segment, of course, in one dimension, just like everything else, because everything in one dimension is a line segment, because that's what it means to be one-dimensional. There we go. That's the word, the phrase, the bit I was looking for. So, how are you guys doing? How are you doing today? Okay, I care. I promise I care about how you're doing, but I do need to stay focused on what I'm doing, which is talking about, I almost said The Hitchhiker's Guide again. It's not what we're talking about today. We're talking about 4-dimensional geometry. Please let me remember that. That's what we're talking about right now. Nothing else. Just 4-dimensional geometry. Just Monica. Did I just make a Doki Doki joke? Yes, I did. Am I proud? No. Okay. We're talking about 4-dimensional geometry. I'm going to say that a million more times. So either get used to it or get off the stream. I'm not trying to be mean. I'm going to say that a million times today. So if you can't handle repetition, you shouldn't be here, because that's pretty much all I know how to do is repeat myself. I'm gonna cry. Why am I here? Why am I here? Just to suffer. That was bad. That was a bad joke. Anyway, what we're talking about right now is 4-dimensional geometry. I'm gonna have to say that 1,000 more times, not just 1,000,000, but 1,000. If you didn't realize how dumb I was before, you have now. You see, I realized about halfway through saying that